I always like to begin this section with an article I read in the New York Times a number of years ago. I'll ask students, what do you think is in that glass? They'll say, Coke, Pepsi, maybe some Guinness. And what's happening as we go from glass to glass to glass? Well, essentially, this is drinking water. And what was on the left-hand side was raw sewage, okay? So you'll go, oh, that is disgusting. Maybe you've read the book, Miss Frizzle Goes to the Waterworks. Some of you have read it. Maybe instead you've gotten a little more technical and really taken a look at articles where they talk about purifying water. Well, why do I bring that up? Because this section is called the autoionization of water. How can I explain the concept? Well, I will take two water molecules, and what will happen is I will have one lone pair of electrons on the water, pluck off a hydrogen atom. So therefore, this has now become our base, and this has now become our acid. And what we do is we produce a hydroxide ion and a hydronium ion. This is a process that water does, and you may think it really happens a lot, but the K for this is very, very small, okay? So let's get started. This is the autoionization of water, section 16.3. Each of these are viable ways to write the autoionization of water. Familiarize yourself so you're not taken by the form of the equation. What happens is a proton in water can form the hydronium ion. And chemists use these two symbols interchangeably. It depends on what we're doing in an equation. So let's take the first equation and write an equilibrium expression. We have our aqueous, but we do not include pure liquids. That takes us to the expression I have written. It has its own K called the Kw. It is the molarity of H plus times the molarity of OH minus, and look at the K. It is much, much less than 1. What? Okay, so Kw is called the ion product constant, and it is specific at a specific temperature, as you learned in the equilibrium chapter. So if I have very pure water, it is a very poor conductor. It doesn't have many ions, and it really is primarily reactants. Why is it that you become electrocuted if you stick your foot in a puddle of water? It's because the water is not pure. It contains many, many ions, all right? And that's why you become electrocuted. By definition, so we only do part of the things in this chapter, a neutral solution has H plus equal to OH minus. You may be solving problems where you are going to assign X's to those species, but it always will hold that something acidic will have H plus greater than OH minus. Something basic will have OH minus greater than H plus. So they may ask a very simple question. If the H plus has this value, is the solution acidic, basic, or neutral? How do you determine that? Well, you take the K for water, 1 times 10 to the minus 14. You divide it by the H plus, 4.5 times 10 to the minus 5. And you come up with the number 2.2 times 10 to the minus 10. You may say, where'd you get that equation? Well, Kw is H plus times OH minus. All I did was rearrange it for the OH minus. Again, algebra, that's all that this is. So if I look at this, I have an H plus of 10 to the minus 5 molar. I have an OH minus of 10 to the minus 10 molar. Definitely H plus is greater, so the solution is acidic. Again, this chapter can really overwhelm you. I encourage you, prepare for lecture, go over notes right away, do homework, let it sink in, ask questions. If you are intending to go, especially to medical school, I mean, the competition is there. You got to know this stuff cold, and now is the time to learn it, not cramming it before an exam. There's just way too much information, okay? What's my last slide here? Well, because students run into a brick wall, I decided to include a homework problem in our lecture. It says, at the freezing point of water, 0 degrees centigrade, a Kw was measured. what are the H plus and the OH minus for a neutral solution, okay, where they're equal at this temperature. I wrote it looks innocent, but has caught many a student. So we still have the same expression for Kw, but now, as I alluded, if I have pure water and I want to make it neutral, I will call each of these x. I will have 1.2 times 10 to the minus 15 is x squared. I will take the square root, and that tells me that's the molarity of a neutral solution at 0 degrees centigrade. Realize they can ask you any temperature, but I don't want you to get caught. And again, this class requires thinking. I often can't go down the total thinking path in a lecture. I tell you what the information is, but now I'm going to try to work in places you might get tripped up.